Welcome to massive open online course on basic principles and calculations in chemical engineering. We are discussing about energy and its forms under module 6. In this module, we will discuss today about the laws and properties of thermodynamics. In the previous lecture, we have described regarding concepts and units of that energy, and also what are the different forms of energy, and also how it can be calculated, that given some idea, and also describe that different forms of energy. And also we have given the general energy balance equation and how that energy balance equation can be used to assess that process for its energy analysis. We will also give more examples on that calculation based on that general energy balance equation in our successive lecture series. Now, in this lecture we will try to even know something more about that energy and its forms. In this case, the thermodynamics and its law, and also different properties of that thermodynamics like enthalpy, entropy, and how those entropy, enthalpy can be calculated will be discussed here. As we know that that energy balance equation for any closed systems, to represent it, we are having this energy balance equation like accumulation, that will be input minus output, and because of that heat input or work output or work input by or heat output, based on these there will be a change of internal energy, and also other system energy change, and based on which we can say that how much energy will be accumulated based on this input or output of the energy of heat and work by machine. So, in that case the system energy will be changed from initial to final state, and because of this energy transferred, this change of this final system energy from its initial system energy can be represented by this general energy balance equation here as shown in the slides. And we can express this equation in this difference form here like this, delta U, that is difference in internal energy and difference in kinetic energy and difference in potential energy, and these changes will be equals to that heat input or output or work done by the system there. And here you can say that this heat energy or that work that is done by the system or on the system, that will change this different system energy, like that internal energy, kinetic energy and potential energy there. So, based on which we can represent this general form of equation. So, in this case you have to remember that if there is no temperature change, even phase change also it is not there, no chemical reactions occur in a closed system, and if pressure change are less than a few atmosphere, in that case we can say that that internal energy will be negligible or almost 0. Now, if a system is not accelerating, in that case kinetic energy that will be equals to 0, and if a system is not rising or falling, we can say that there will be no potential energy change. And also if a system and its surroundings are at the same temperature or the system is perfectly insulated, then we can say that there will be no heat supply it there, or it will be coming out from the system. And work done on or by the system is generally accomplished by movement of the system boundary, and in that case if there are no moving parts or electrical currents or radiation of energy of this type at the system boundary, then we can say that this work will be equals to 0. So, if we express that general energy balance for an open system, we can have this energy input and in energy work as output, whereas here in the initial state that the kinetic energy, potential energy, and what will be the internal energy, also how this pressure there in the inlet change, and also volume of that inlet condition. Similarly, at that outlet condition, what are those system variables are there as an energy. So, based on which we can write this final form of general energy balance here. So, this will be your change of potential energy, change of kinetic energy, change of potential energy. Here this that this work done by the fluid system here, that will be represented by this P out into V out minus P into V dot in, then it will be equals to here as per equation given. So, this is your that final forms of general energy balance equation for an open continuous system. So, in this case rate of final system energy minus rate of initial system energy, that will be equals to rate of net energy transfer to the system. Now, this rate of initial system energy can be represented by these terms, and the final system energy can be represented by these terms, and energy transfer, that will be Q dot minus W s dot. This W s dot is basically that shaft work, and this P 1 V 1 P in V in and also in the outlet P out V out, the difference of this that work done by this changing of volume or pressure by this fluid flow, it will be regarded as that work done by the fluid, and in this case this that work done by the shaft and work done by the fluid flow, then it can be regarded as total work energy as W. So, that is why we can that write here that W will be equal to W s plus W f l. Here in this case W s dot is shaft work, the rate of work done by the fluid on a moving part within the system, example like piston, turbine and rotor. Similarly, W f l here this is a flow work, that is rate of work done by the fluid at the system outlet minus the rate of work done on the fluid at the system inlet. So, this summation of this shaft work and the flow work will be regarded as the total work done by the system. This that difference in that heat energy supplied or this work done by the system, what is the difference? That difference will give you that change of internal energy, kinetic energy and potential energy, and also we can say that will be added to that that change in flow work. So, net input rate to the system will change the rate of net and change of energy in the system as an output there. Now, the energy balance for an open process system can also be actually expressed by this equation here in terms of different forms there. So, delta U dot plus delta K E dot plus delta P E dot plus delta to P V dot, that will be equal to Q dot minus W dot. So, in this case we can say that this delta U dot is the internal energy change, delta K E dot is kinetic energy change, and delta P E dot is potential energy change, and delta P V is the flow work performed on the system in order to push the fluid in or out of the system. And here Q dot is the rate of heat energy in, and W S dot is the rate of work done by the system as output. And you have to remember that this summation of this internal energy change and this flow work performed on the system will be equals to or will be regarded as enthalpy of the system. So, this enthalpy change will be defined as delta U dot plus delta P V dot. So, this delta H dot is called enthalpy change. So, the enthalpy that will be equal to then internal energy plus that pressure into volume. We can say that the steam turbine is an open system where you can apply this energy balance equation to solve those problems. Even other problems also you can apply this energy balance equation. We will do some problems in our next lectures there with this energy balance equation. So, before going to use this energy balance equation for a particular chemical engineering process unit, we have to know some thermodynamic properties and its law, because here this internal energy, enthalpy change, all those are basically thermodynamic properties. So, these how these thermodynamic properties are defined and how to calculate, we have to learn first. Then we can use these these thermodynamic properties of like this internal energy, how enthalpy will change, and also how potential energy, kinetic energy, all those things are change, based on which we will be able to do the energy balance for a particular process. So, let us know something about that laws of thermodynamics. Here the laws of thermodynamics define actually with physical quantities like equilibrium, temperature, energy and entropy that characterize thermodynamic systems at thermal equilibrium. So, there are different laws of thermodynamics that will give that idea of that physical quantities in terms of equilibrium, temperature, energy and entropy, which will characterize this thermodynamic system. In this case we can say the 0th law of thermodynamics, first law of thermodynamics, second law of thermodynamics, like this. Now, what is that 0th law of thermodynamics here? According to this law, it is said that if two systems are each in equilibrium thermally with a third system, then you can say they are in thermal equilibrium with each other. So, this law helps define the concept of temperature actually. So, this temperature will higher temperature will try to distribute in such a way that it will make a reach of that equilibrium of these two temperature of higher to lower. So, based on which we can say that if suppose two systems are in contact with each other in a thermal equilibrium condition with third one, then of course, this third system will try to come in a thermal equilibrium so that they are in equilibrium thermally with each other. So, this is called 0th law of thermodynamics. Whereas first law of thermodynamics gives you the that concept of conservation of energy. In that case, when energy transfers as work, as heat or with matter into or out of the system, then systems internal energy as per the law of conservation of energy will be there accordingly. So, when energy transfers as work, as heat or with matter into or out of a system, the system internal energy will change accordingly to give you that total energy of the system without destroying of this. So, that is why this first law of thermodynamics will give you that how much energy will be forms, internal energy will be forms based on the that work done on the system or work done by the system, or heat energy will be supplied, or that energy may be transferred by the matter also. So, based on which you can say that how that system will be changed in its energy. Whereas, the second law of thermodynamics says that processes that involve the transfer or conversion of the heat energy, that will be irreversible, and it is about the quality of the energy, and it states that energy which is transferred or transformed and more of it is generally being wasted. And according to this second law, it is also said that there is a mutual tendency of any isolated system to actually degenerate into a more disordered state. So, we can say that according to this second law of thermodynamics, that whatever transfer or conversion of that heat energy will be there, you cannot make it to reversible to its original state. So, it is called the irreversible process. And in the case of that third law of thermodynamics, that there will be a change of entropy because of that conversion of heat energy into its other forms, like internal energy change or potential energy, kinetic energy change there. You will see that this phenomena of changing this state of this system, that will approaches a constant value as the temperature approaches absolute 0. So, all this that whatever internal energy will be changed by supplying that heat energy from the surroundings to the system, and in that case this internal energy whatever it is changed, that actually depending on the temperature change. So, whenever you are talking about the some characteristics which are being changed in terms of that internal energy, or you can say that some environment will be changing, which will be called as that entropy, that depends on the temperature. Now, you will see that if there is an inequilibrium condition of the temperature distribution inside the system, you will see there will be a certain characteristics of the system that will be represented by the entropy. Now, that entropy will be reaching to absolute 0 when temperature approaches that absolute 0, that you will see that the entropy of the system will recess to a constant value. So, that is that this is something qualitative things, that some the characteristics of that systems will change, and it will reach to a constant value when this temperature will recess to its absolute 0. Now, this entropy of the system at absolute 0 is typically close to 0, and in that case the entropy of the perfect crystal is regarded as 0 when the temperature of the crystal is equal to the absolute 0. For the pure substances like pure crystals, in that case this entropy will be 0 at its absolute 0, whereas in other cases you will see that at its absolute 0 temperature, this entropy will recess to a certain value, that is at constant value. You cannot actually get that absolute 0 entropy there, because of that any systems of real system, you can say that may not have its temperature converted into absolute 0, because there anyway there will be a certain that frictional energy and movement of that molecules will give you certain heat energy there. So, at that cases you will see that if this temperature is going to or tends to or approximately equals to 0, that you can say that this entropy will be reaching its constant value. And how this entropy actually quantitatively can be estimated. So, in this case here one that mathematical representation here shown here, that how this entropy change can be calculated. If you are changing your heat energy for a small amount, you will see at a particular temperature, you will see that at that temperature that entropy change will be defined by that change of heat upon at its temperature. So, we can say that entropy is basically a physical measure of the lack of physical information, that is called characteristics, how that system will change, about the microscopic details of the motion and configuration of a system, when only the macroscopic states are known to you. So, we can observe that there is a change of that entropy only by change of that macroscopic states, whereas this entropy basically happens when there will be a microscopic change of this physical activities there, or you can say that some characteristics there. And like that if suppose there is a motion of that particles, even if you are changing the configuration of the systems there, then microscopically you can say that because of this microscopic change of this motion or system configuration, you will see that there will be a change of entropy, and that entropy you cannot actually measure by that microscopic change, but only you can realize it by the macroscopic state change of that system. So, according to that second law of thermodynamic, that laws or you can say thermodynamic behavior in a theoretical and fictive reversible heat transfer, we can say that an element of heat transferred, that is delta Q, is the product of the temperature, both the system and the sources of destination of the heat, with the increment delta S of the systems that conjugate variables, and which is called that entropy. So, as per this concept, the mathematical representation of this entropy can be expressed as delta Q will be equals to T into ds. Also, this entropy can be a measure of a system's thermal energy per unit temperature, that is unavailable for doing useful work there, because in this case this work is obtained from the order of that or you can say regular fashion of that molecular motion, and also this can be a measure of that molecular disorder or randomness of the system there. So, this basically that how that systems environment will be changing based on that heat energy supplied at a particular temperature, and this may change of molecular order or disorder or fashion, or you can say some configuration of the systems. So, based on which this entropy can be measured. Another important thermodynamic properties you can say for that energy consideration is the enthalpy. It is generally that how much internal energy will be changed there, and also if you supply or if you apply some pressure, and because of which if is there any that volume of that systems will change, you will see there will be a change of system energy because of that applying of that heat energy there. So, that change of that systems energy in terms of internal energy and also flow energy there, we can define this thermodynamic property as an enthalpy. Now, this enthalpy can be actually known as qualitatively and also quantitatively also. Qualitatively, we can say that it is a thermodynamic property of a system that will be capable to do non-mechanical work and capable to release some heat. Or you can say that the enthalpy is a measurement of energy in a thermodynamic system, which is equivalent to the total heat content of a system. So, it is a function of state and its value depends only on the starting and final states of the system. And quantitatively we can define this enthalpy as the sum of the internal energy and the product of the pressure and volume of a thermodynamic system. This is basically the summation of internal energy and the flow energy there. So, this enthalpy can be denoted by H, and it can be defined by this equation given in the slides. Here H is enthalpy, U is internal energy, and P is the pressure and V is the volume. Whereas a specific enthalpy can be defined as here or it can be denoted by H hat. So, H hat will be equal to H by M, that means per unit mass what will be the enthalpy there, it can be regarded as specific enthalpy. So, this specific enthalpy can be defined as H by M as per this equation here. So, H by M will be equal to U by M plus PV by M. So, H by M is basically that specific enthalpy, and this U by M can be denoted by U hat, it is called specific internal energy, and here P into V by M, that you can regard it as P into V hat. Here V hat is for the specific volume of the system. So, we can then represent this specific enthalpy by this equation here. Now, let us do an example for this calculation of specific enthalpy based on that internal energy change there. Now, if we say that a system under a certain condition at which that the rate of enthalpy is transported by a stream with a molar flow rate of 200 kilomole per hour. In this case, the specific internal energy of that system of a gas at 25 degrees Celsius and 1 atmosphere is 3.79 kilojoule per mole, and also specific molar volume is given, that is under same condition is 24.5 liter per mole. So, under this condition of this system at a rate of flow of 200 kilomole per hour, a stream which will transport this enthalpy change because of this internal energy and this pressure or flow energy, and what should be that rate of enthalpy will be there, that you have to calculate. Now, in this case we know that the specific enthalpy is defined as that summation of specific internal energy plus that P into V hat. So, according to this equation, if you substitute this internal energy that is given in this problem, specific internal energy is given, and then substitute this pressure is in 1 atmosphere. So, you have to convert it to Newton per meter square, and also what will be the volume. This specific volume is what will be that, this is given here, the specific volume is 24.5 liter, then you have to convert it to meter cube. We know that 1 meter cube is equal to 1000 liter. So, you can say that after conversion of this volume will be equal to 24.5 by 1000, it will be meter cube per mole then, and 1 atmosphere to be converted to Newton per meter square just by multiplying 1.01325 into 10 to the power 5. And then finally, the unit for this specific enthalpy will be coming as joule per mole, and final value after calculation it is coming 627.46 joule per mole. So, the total enthalpy transport rate can be then that calculated by this equation here. Total enthalpy transport rate, it will be equal to specific enthalpy into molar rate. So, here molar rate you have to convert it to that like this. Here molar rate is given 200 kilomole per hour, then you have to multiply again into 1000, it will come to that mole per hour. If you substitute the value of, that is number of moles there, with this this specific enthalpy of 6272.46, then finally you can have this 1.25 into 10 to the power minus 10 to the power 9 joule per hour, that will be equal to 348.47 kilojoule per second. And this calculation of enthalpy change, whatever you are getting here based on that internal change, internal energy change, that change in enthalpy can occur because of change in temperature, change in phase, mixing of solutions and reactions. And this enthalpy also can be regarded as a sensible heat. This is basically a heat transfer to raise or lower the temperature of a material in the absence of phase change. And this sensible heat change is basically determined by using a property of matter called the specific heat capacity at constant pressure or constant volume, and it is represented by that joule per mole per K or calorie per gram per degree Celsius. So, in this case this sensible heat basically that one type of enthalpy change because of the temperature change. Now, that enthalpy change or sensible heat can be calculated based on that temperature change, and that temperature change will give you that sensible heat based on that how much materials actually being heated, and also what will be the heat capacity or specific heat capacity of that material. So, based on which we can calculate that sensible heat as that delta H, or you can say delta Q, in that case that will be equal to Cp into dT, where this Cp is the specific heat capacity there at constant pressure, and also you can get that internal energy change based on that temperature change also, and for that also how that specific heat capacity at constant volume is changing, that also to be required to know for that particular material. So, in that case specific heat capacities for most substances vary with the temperature, where the values of Cp vary for the range of the change in temperature, and within a certain range of temperature that specific heat capacity will change with respect to temperature. So, according to that there will be a there is a correlation to calculate that specific heat capacity for constant pressure and specific heat capacity for a constant volume. Since it is a temperature dependent, but for the specific heat capacity at constant pressure it will be non-linear. It generally follows that polynomial equation of temperature, and it is expressed as by this Cp will be equals to A plus Bt plus Ct square plus dT cube. Here T is the absolute temperature, or you can say that in Kelvin, and A, B, C and D are the constants, and these constants depends on the material, or you can say that gas or liquid like that. And for that specific heat capacity for a material at constant volume will be a linear function of temperature, and it will be Cv is equal to A plus Bt. Here A and B are also constants which are depending on the nature of the substance or matter or material, you can say, and these coefficients you can get it from your textbook. It is given in the appendix for different materials what will be the value of A, B, C and A and B for that specific heat capacity for constant pressure and volume respectively. As an example, for nitrogen gas at 1 atmospheric pressure, this specific heat capacity of that nitrogen gas in kilojoule per mole per degree Celsius is given here in the slides. Here see how this A, B, C are there, this A, B, C and D value for this specific heat capacity at constant pressure. So, accordingly you can say that this A, B, C and D coefficients would be varying with other gas, even other materials also. So, those you can find it out from the textbook, and it is given in the appendix. Now, for ideal gases, you will see there will be a certain relationship between these specific heat capacity at constant pressure and specific heat capacity at constant volume. So, this relationship here as expressed as Cp will be equal to Cv plus R. Here R is called universal gas constant. For liquids and solids, this Cp will be equals to Cv. According to Koff's rule, this Cp can be estimated for a particular materials based on their atomic composition. Now, how you can get that specific heat capacity for a mixer? You will see for any chemical engineering operation, you will see there are several components will be mixed for its actually processing to have certain product. In that case, you have to find out what should be the specific heat capacity of that mixers. So, the overall heat capacity in that case you have to define, since the overall this heat capacity will be changing from its individual components, and since there is a mixture of different components and it will have different specific heat capacity, but you cannot directly add those that specific heat capacity of all components there. It depends on also mole fraction of all those components in the mixture. So, overall specific heat capacity can be defined as that summation of that specific heat capacity of that pure material into its mole fraction in that mixture. So, it can be written mathematically by this equation as given in the slide here. Then Cp mix at particular temperature, that will be equal to summation of Xi into Cpi into T. Here Xi is called mole fraction of component psi, and Cpi is the specific heat capacity at constant pressure of that particular component. Similarly, you can express that specific heat capacity at constant volume for the mixer, and this overall heat capacity can be expressed again by this equation as fashion of earlier that equation, that will be equals to summation of Xi into Cvid. Here in this case Xi again that mole fraction of that components in the mixer, and Cv is the specific heat capacity of that particular components at constant volume. Here index I ranges overall over all of that components of the mixer, and Xi is the mass fraction, or it may be mole fractions also according to your calculation. Now, enthalpy change as a result of temperature, how it can be actually calculated? Whenever temperature will be changes, then how enthalpy will also be changed and how it can be calculated. Basically, there are several methods you can calculate this enthalpy, based on which you can say that if you know that specific heat capacity of a particular material, then this enthalpy change can be calculated based on that temperature difference from the reference temperature by this equation here given in this slide. Here delta H will be equals to m into Cp into T minus T reference. Here suppose the temperature is increasing from T reference to that a final temperature of T, and if you know the material property of its specific heat capacity at constant pressure, and also what will be the moles or mass of that materials, then you can easily calculate enthalpy change based on this temperature change from its reference temperature. And this you can express this in integral form also. Based on this integral form, we can write here delta H dot, that will be equal to m dot integration of Cp dt. Here in this case, since Cp is a function of temperature, so within a certain range of temperature, what should be the enthalpy change you can directly get after doing integration of that function of specific heat capacity at constant temperature with temperature, and also you have to multiply it with the amount of that material there. So, by this equation you can easily then calculate what should be the enthalpy change if that Cp will be changing with temperature. Now, you know that Cp capacity is the most substances vary with the temperature, where the values of Cp vary for the range of change in the temperature. So, this functionality of that Cp can be expressed by this polynomial equation of function T. Let us do an example for this. You need to calculate what should be the change in enthalpy of 100 gram per second brine solution heated in a counterflow heat exchanger from 20 degrees Celsius to 80 degrees Celsius. If the average heat capacity at constant pressure is 3.12 kilojoule per kg. So, in this case you have to first calculate the temperature change there in absolute temperature, and also you have to first calculate what should be the flow rate there, and then what is the that specific heat capacity there. If this specific heat capacity is constant over a range of that temperature, you can directly use that specific heat capacity of that constant value. Otherwise, you have to use that functionality of specific heat capacity which is given earlier as like this: Cp is equal to A plus Bt plus Ct square plus dt cube, and after substitution of that Cp value within a range of that temperature of, here it is given 20 degrees Celsius to 80 degrees Celsius, then you can get this that enthalpy change at a rate of 18.72 kilojoule per second. So, in this way you can actually calculate how this enthalpy change will be there if the specific heat capacity will be changing within a certain range of temperature. Also, according to that second law of thermodynamics, you can say that there will be a change of internal energy if you supply some heat energy into the system. In that case, the change in internal energy, again it will be a function of heat capacity at constant volume, and that heat capacity again will be a function of temperature there. So, according to that you should multiply the mass by that heat capacity as follows by this equation to get that internal energy change. Now, let us do an example for this internal energy change also. In this case, if a closed rigid vessel that contains 200 kg of fluid is what is heated from 20 degrees Celsius to 150 degrees Celsius. In this case, you have to calculate the heat required for this purpose. The constant volume heat capacity of the fluid is given by the following relation here for that particular material. As per general energy balance for closed system, in this case there is no change in kinetic energy, there is no change in potential energy, also there is no moving part there. So, in that case we can say that there will be no shaft work done on this system, and as the system is a rigid vessel, we can say that mass is constant there. So, according to that we can write this energy balance equation as Q will be equals to delta U, where this delta U will be calculated based on this equation here. According to that specific heat capacity change with respect to temperature. So, after substitution of this heat capacity at constant volume and integrating within the range of temperature of 20 degree to 150 degree Celsius, you can get this internal energy change as 24312 kilojoule. Now, how to calculate the enthalpy of ideal mixture? You have to remember that for an ideal mixture the enthalpy of mixing will be 0. In this case, if the mixing itself does not contribute to a change in enthalpy, the specific enthalpy of the mixture is simply equal to the sum of the enthalpies of the mixture components. But the condition is that if the mixing itself does not contribute to a change in the enthalpy. So, we can represent this mixture enthalpies as H hat mix T, that will be summation of xi into Hi hat. Here xi is the mole or mass fractions of that components in the mixture, and Hi hat is the enthalpy, that is specific enthalpy of that particular component psi. In this case, the assumption that a mixture behaves ideally nearly always works well for mixtures of gases, and it also works well for liquid mixtures. When the species being mixed are chemically similar, such as two aromatic species or two linear hydrocarbons. Now, enthalpy of non-ideal mixture also to be assessed there, because mixtures are not ideal anywhere in real application. This is because of the mixing of two or more species alters the molecular interactions, which is experienced by the molecules being mixed there. Thus, the internal energy, and hence you can say that there will be a change of enthalpy. And for non-ideal mixture, that enthalpy change for that mixture can be represented as specific enthalpy change of that mixture as that specific internal energy of the mixture that is changed, plus how that flow work or flow energy can be changed for that mixture there. So, we can expressed by this equation that is given in the slides, and in this case very interesting that the change of volume of this mixture will be different from that summation of that volume change of individual components based on its mole fractions. So, in this case delta V mix, that will be equals to V mix minus summation of xi into Vi here. So, it is important to know that how that volume of that mixture will be changed, that is specific volume of that mixture will be changed if there is a change of individual specific volume of that components will be changed, and in that case what will be the total mixture volume, that is specific mixture volume, that you have to subtract those summation of specific volume of that components there. In this regard, you have to remember also that there may also be a change in volume when two species are mixed. In this case, the final volume of mixture V does not equal to the sum of the volume of the components that were mixed together. So, this is very important to note here. Let us do an example here. Let us see that thousands kilomoles per hour of a liquid mixture of 70 mole percent acetone and 30 mole percent benzene is heated from 10 degree Celsius to 50 degree Celsius in a shell and tube heat exchanger using a steam as the heating medium. In this case, you have to calculate the changes in specific enthalpy of acetone and benzene mixture. In this case, since the mixture contains 70% acetone and 30% benzene, you have to first find out what will be the moles of that acetone and benzene. Since total amount is given to you as 1000 kilomoles, so in that case the moles of acetone will be equal to 700 kilomole, whereas moles of benzene will be equal to 300 kilomole. The change of mixture specific enthalpy can be written as here in the slides So, in this case if we substitute that mole fractions of individual components and enthalpy specific enthalpy change of individual components, we can get that total change of mixture specific enthalpy there. So, it can be written as here enthalpy specific enthalpy change of mixture will be equal to 0.7 delta H acetone hat and 0.3 into delta H benzene hat, that can be represented by this equation here, integration of Cp mix into dt within a range of 10 degree Celsius to the 50 degree Celsius temperature. Now, you have to then calculate the Cp mix here, specific heat capacity of the mixture then given by this equation here, and then Cp acetone can be calculated based on this equation, and Cp benzene can be calculated based on this equation, and then after substitution of this heat capacity of acetone and benzene and after rearranging we can get this Cp mix will be equal to this, and then substitution of this Cp mix in that integral form, and after integration and substitution of this limit of this 10 to 50 degree Celsius, and finally you can get this 5200 joule per mole. So, in this way we can calculate what should be the specific enthalpy change of the mixture. Similarly, we can calculate the change of internal energy of the mixture. In this case, the changes in specific internal energy associated with that mixing processes, which is the internal energy per amount of mixture, that will be minus the internal energy of the species that were mixed there. So, in this way you can calculate here given as equation in the slides. In this case U I hat is the specific internal energy for pure species whose fractions are given as xi. So, from this equation you can easily calculate what will be the internal energy change of the mixture. Similarly, you can express that how heat will be changing for solution based on that enthalpy calculation, that is called as heat of solution or enthalpy of the solution. So, enthalpies of mixing are often expressed in terms of that heat of solution. It is the change in enthalpy that results from dissolving 1 mole of solute in certain moles of liquid solvent at constant temperature. Now, in this case when 1 mole of solute is dissolved in an infinitely large amount of solvent, the heat of solution will be approaching to a limiting value, which is known as heat of solution at infinite dilution. You also have to sometimes calculate the enthalpy change whenever there will be a change of state, there will be a change of phase, like that suppose liquid water is becoming into its vapor. So, in that case what will be the change of enthalpy whenever it changes its phase from liquid to vapor, or sometimes solid is becoming liquid, then how the change of enthalpy will be there from its phase change from solid to liquid. Similarly, from gas to liquid, whenever it will be changing, how that enthalpy will be changed, that you have to calculate. So, in this case you have to remember that the state of a system can be changed, for example, by increasing its temperature or changing its composition. Properties of the system whose change depends only on the initial and final states of the system, but not on the manner used to realize the change from the initial to the final state as referred to as a state properties. In this case, whenever this phase will be changing from one phase to that another phase, the respective enthalpy can be regarded as like latent heat. Here like phase changes like evaporation and melting are accompanied by relatively large changes in internal energy and enthalpy, and in that case you have to refer at what will be the change of that heat or change of that internal energy, and that heat change, and which will give you that result of that enthalpy change at a constant temperature for changing its phase from one to another. So, that heat of change of that phase is called latent heat. There are different types of latent heat, like latent heat of vaporization, which is actually required to vaporize a liquid, latent heat of fusion, which is required to melt a solid, latent heat of sublimation, which is required to directly vaporize a solid. So, this latent heat of vaporization, latent heat of fusion, latent heat of sublimation, this is basically a enthalpy change, temperature change at a constant temperature when there is a change of phase from its original to another. Now, latent heats are in general a function of pressure and temperature. However, they depend much more strongly on temperature than on pressure. Therefore, we can say that when calculating heat associated with a change of phase, it is important to ensure that the latent heat value used for that calculation, whether it is that for that actual temperature or not, at which this phase transformation occurs. So, in this case, remember that latent heat of vaporization cannot be the same as what it is in 30 degree centigrade or some 30 degree Celsius, which is at 100 degree Celsius. So, we can say that the latent heat of vaporization at 30 degree Celsius is not same as at 100 degree Celsius. Now, sometimes you will see that in a particular chemical engineering process there will be a process unit, and that process unit will have several input and several output streams. Now, in that case, in a particular streams there will be a mixture of components, and also you can say that components may be in the inlet, and that components may be in the outlet streams also. Sometimes if there is no reaction, only physical operations will be there. In the inlet streams, whatever that components will be there, after a physical operation there may be that some unwanted or that unused components also will be in the outlet streams. So, there will be a mixture in the inlet outlet streams of that several components. So, in that case, that this how that enthalpy change will be there based on that different mixing in different streams there. Let us here see one process unit given here. There are three that streams 1, 2, 3 here has mentioned in the slides. In stream 1 here in a mass flow rate it is given, some mass is coming, and then in the outlet streams that the mass 2 and mass 3 are coming out there. So, in this case you will see that there will be several components will be coming in and coming out from this inlet and outlet streams. So, according to that you have to calculate that enthalpy change because of this final stream and this inlet streams enthalpy. So, what will be the enthalpy change in the inlet streams? First you have to calculate, and what will be the change of enthalpies in the outlet streams. It may be in that mixture of components in each streams also. So, the enthalpy change because of this change of enthalpy in different inlet and outlet streams, we can say that this enthalpy overall enthalpy change will be equals to 0. So, we can have this equation as like this: summation of enthalpy in outlet streams minus summation of enthalpy in the inlet streams. There may be more than one inlet. So, accordingly you have to sum it up the total enthalpy change in the inlet streams. So, the general energy balance for an open system after applying that assumptions is reduced to like this, delta H will be equals to 0. So, accordingly we can say that delta H will be equals to here H3 minus H1 minus H2. H3 is basically that, what is that, outlet streams, H1 and H2 are the inlet streams there. So, according to that enthalpy of those streams, we can simply write this here, delta H that will be equals to H3 minus H1 minus H2, that will be equals to 0. And also you can represent it as this equation here, where H3 hat, H1 hat and H2 hat are the specific enthalpy at its that inlet and outlet streams there. So, we have learned here some thermodynamic properties like internal energy, enthalpy, latent heat of vaporization, and also how this enthalpy can be calculated, how enthalpy change can be calculated for the mixer components, how enthalpy can be calculated in a specific process unit having more than one inlet and outlet streams. Also internal energy, how it can be calculated, and also that enthalpy and internal energy, how it can be calculated from the specific heat capacity which is a function of temperature, all those things. So, I think you understood little bit about this this enthalpy change and internal energy change and how it can be calculated from the energy balance equation. I would suggest you to go through this textbook and reference books for more information about those thermodynamic properties. And in the next lecture we will try to discuss more about that enthalpy. There are some heat of solution, heat of formation in the reactive mode, how that enthalpy will be changing, and also in internal energy how it will be changed, that will be discussed in the next lecture. So, thank you for your kind attention.